Andrew, are you here? Jack, middle. James, middle. Hey, can you guys keep it down just a little so everyone can hear their names? Jeffrey, podium. Jordan, middle. Did I miss anyone? Seems crazy anyone could be missing because it's so crowded. Annabelle? Okay. Oh, there you go. Find your piece. Okay. Let's see what people want to talk about today. Number 25. There's so many things wrong with 25 is what I'm hearing right now. Number 19, we've got some factoring. I don't see any little questions yet that I can just dispatch. But I also have some material that I want to tell you, just a few things from the section that you might be confused about that I thought you might want to talk about. So in particular from the reading. So that's what I'm going to start with. Keep adding questions here while I'm talking, and then we'll know what we're going to talk about today. Let's see. Okay, how's everybody's day today? I'm tired. You locked yourself out of your room? Oh, well, that sucks. What else is going wrong for people this week? Anyone? I just came from like a really contentious meeting where I was yelling. So I'm trying to be polite. But so I'm cool now. It's all good now. Okay. So, we did that one. Okay, so in the reading, there are two theorems. Once somebody asked me, do we have to remember the names of the theorems or the numbers of the theorems? And I said, oh my God, no. But these two you actually do. So these are two very famous theorems, the extreme value theorem and the intermediate value theorem. And each of them says something very obvious in a very fancy way. Okay. Of course. So say of course. I agree. So the extreme value theorem, what it says is that if you have a function that's continuous on a closed interval, that's like the nicest possible function you could have. It's like you have, I think of it like you have a thumbtack in a bulletin board, and then you have another thumbtack, and you put a piece of string connecting one thumbtack to the other, right? So it's actually grounded at the ends and connected completely in the middle. It's not broken. It doesn't like go off to infinity in the middle or at the ends. It doesn't have a hole. It's continuous on the whole closed interval from thumbtack to thumbtack. If that is true, somewhere the string is the highest and somewhere the string is the lowest, right? So like if you just arrange this wire or string on the board, somewhere there's a place, and by somewhere I mean an X value, and I'll call it capital M. Somewhere there's a place where the height of the function, which is f of m, is the most. And that's actually exactly what this theorem says. If f is continuous on a closed interval, you can find a capital M inside the interval so that the value at m is the maximum value of the function. And it might be achieved more than once, that's okay, right? But there's at least one place where the function is the highest, and then little m is a place where the function is the lowest. And notice in this picture, little m happens to occur at the end. That's also okay, okay? So the little m and big M could be in the middle or they could be in the end. Very obvious fact. Does anybody doubt this fact? That there's a place where the function would be the highest? Or the place where the function, I don't doubt that fact. How about this one? Intermediate value theorem, same setup. It says you have this, thumbtack to thumbtack with a piece of string, continuous function on a closed interval. And then you look at the heights of the thumbtacks. And this theorem says the string goes through every height between the two thumbtacks. So think about it. If you tie a string to this thumbtack and you tie a string to this thumbtack and you erase it on your bulletin board somehow, is there any way to get down here without going through every height in between? No, your string can't just teleport over there, right? It has to go through all those heights, those intermediate values. The heights are the values. Intermediate means between, okay? It would be really great if this could be called the between heights theorem, right? That would make a lot more sense, but we don't do that for some reason. And instead of the extreme value theorem, the highest and lowest point theorem, right? How much easier would math be if we named things like that? But I guess there's probably reasons why people don't. Has to sound fancy. Hey, never hurts to sound fancy, right? If you can bring the fancy, then you get a job, right? That's good. It's good to have the fancy, but also like math people like to name things in like a really general way. So like the concept of a value for us is a height, but in other contexts could be something else, right? The extreme value, you know, they don't want to say whether it's high or low because in a different context, it might not be height related. You know, math people are just super general, right? But it does make us sound also super fancy. Okay, so that's what these two theorems say. And who believes that these theorems are true? Yeah, okay, I'm not trying to trick you. They are true. But what I want to tell you is if you look at the proofs of these in the reading, they're not there because the proofs are too hard. It's too foundational a thing to even talk about. And they both rely on something called the least upper bound axiom, which is this fancy property of real numbers that if you go on to be a math major, you might learn about. Like it's about the unbrokenness of the real numbers and the continuity of numbers themselves. It's really like there's a deep question happening there. And we're not going to do that. I just want you to know that that's true. And these theorems will be very important to us. And in particular, the intermediate value theorem is a very popular theorem to apply when k is 0. So this is saying that for every k between f of a and f of b, there's a place where the function is that high, right? The k equals 0 case is actually what we use when we do a problem like this. So back in chapter 0, when we wanted to find where this function was positive or negative, we would put the roots of the function, k equals 0, on the number line, and we would just check these chunks, and we could be confident that the function would be negative on the whole chunk or positive on the whole chunk, on every chunk. And it was actually the intermediate value theorem we were using because let's say, for example, it could be partially negative and partially positive on this chunk right here. Well, that's like putting one thumbtack down here and one thumbtack up here. At some point, the function is going to have a root, but it doesn't because that's what, oh, these are the only roots, okay? So we're using these things like the intermediate value theorem and the extreme value theorem all the time. There's a few homework problems in there that are going to torture you. Definitely read the resources about those. Definitely ask in Piazza. We'll have a conversation about those if you like. The intermediate value and extreme value theorem homework problems you might need some help on. Okay. Any questions about that? These theorems? Okay. Okay, so let's look at why can't I press buttons? Okay, there we go. So the video did not load. Oh, well, let's check that out first. I want to see what happened. You mean the video and the resources for number 10? All right, let me go here. Might be the calc clip ones. Yeah. You know what? I think you have to be logged into WebAssign for it to work. Okay. Because I think let's see if that's true because I'm not logged into WebAssign, and so it shouldn't work for me. Okay. So let's see. Problem 10 is probably in here somewhere. Problem 9, problem 10. This one. Problem 10. Yeah, this one probably isn't the one. Let's see if it's the next one. Yeah, I bet it was. Well, okay, we don't actually have to illustrate it here, but I think that you have to be logged into WebAssign for that to work. The same thing is true if you click on those little links for the definitions in the book and they don't work. I think you have to somehow be logged into something for those to work. But thanks for bringing that up. Oh, that doesn't look right because I didn't press the right button. Okay, well, that's fine. Number 10, we sorted that out. Number 19, don't know how to deal with factoring. Number 25, of course, is, oh, guess what? It would be a good idea for me to be. It would be a good idea for me to be logged into WebAssign is what it would be a good idea for me to be. And I apologize, I'm slightly less prepared because I had to yell in a meeting. Okay, so just, you can just watch me log into WebAssign. It's a fun break for you this morning. You can do breathing exercises. I'm working on that. Okay. Let's see. We're doing 6. Sorry for that delay. Okay. 25. Let's just take a look at what 25 even is. Describe words continue. Oh, we definitely could do this one. That's a good one. Okay, I like this one. Let me present this and make it small so we can see both at once. Okay, and then number 19. Yeah, factoring the square root. This is a good one. Oh yeah, this one sucks. Yeah. Okay, I can see why you'd have a problem with this one. So I think we're going to do 19 at the board, but we'll start with 25. Let's just talk about number 25, and then we can work on number 19. Let's see, how would I, ooh, okay, great. Okay, so we've got this function here, and we have all these things to answer about it. And in particular, we want to describe where it's continuous. Now, I don't know why the WebAssign people made the problems this way, but this is like the one you should probably answer last, right? I mean, in order to answer this question, you have to compute the left and right hand limits, right? I mean, that's what you have to do. Maybe they're thinking people might just graph it and get the answer, and then they were going to say, okay, no, buckle down, really find the answer. Maybe that's what they mean. But we have to compute these left and right limits at 5 as part of our work of determining where the function is continuous. And then if you notice here, it's asking us about 2 points, x equals 5 and x equals minus 5. Did anyone see this discussion in Piazza? There was a discussion about this in Piazza, but in that discussion, the x was 4 and minus 4. And the question was, I get why at x equals 5, we have to look. Why do I have to look at x equals 5? Why would it maybe be discontinuous at x equals 5? Yeah, there's a break there, right? Like, I mean, that's where the two pieces are. So at x equals 5, we clearly are going to, it might not be discontinuous, but we should look, right? Why are they even asking about x equals minus 5, though? What's wrong with negative 5? 0, that's right here. In the first piece, if x is negative 5, you actually have a divide by 0. So there's a different kind of discontinuity that could happen there. Instead of a breakpoint discontinuity, the piece itself could have a discontinuity. So we're going to compute the left and right hand limits at 5, and we're also going to consider what happens at negative 5. I think we'll start with this, computing the left and right limits at 5. And let's just write one of them out very carefully. So like limit as x goes to 5 from the right of the function. Remember, the reason I'm calculating this is because the function is continuous if its limit is equal to its value. Okay, so I want to compare this limit and this limit, 5 from the left, with the value at 5. So I don't know why my 5 looks so weird. Please let me redo it. If these two are the same, then the limit is whatever that thing is. And if that thing is the same as the value, then the function is continuous. That's what we're looking at. Okay, if I look at the limit as x goes to 5 from the right, which piece of the piecewise function am I thinking about? The top piece or the bottom piece? I'm looking at, so 5 is here, I'm coming in from the positive side, which piece of the function am I on? Bottom piece. Okay. Oh, I don't know why I did that. Now, that's a continuous function, just this little function, right? Everywhere it's defined, its limit and its value are the same. Thought of another way, I can solve limits like this just by plugging in. If I plug in and I think that happens, that's the answer. So that's what I'm going to do. I'm going to plug in and I'll get 5 squared minus 5. If you're curious, and this will come in handy later, it's really not exactly 5, right? But we're thinking of something that's approaching 5 from the top, but we don't actually need to consider that here. It doesn't matter. We get 25 minus 5, which is 20. Please tell me if I make an arithmetic error, but I don't think I do. On the other side, I've got the limit as x goes from 5 to the left. As I approach 5 from the left, what function am I using? The top or the bottom? Top one, right? So 8x squared is here, and then x squared minus 5. It seems like a miracle if that would equal 20, but let's just find out. I have 8 times 25 over 5. What's that? Okay, let's just back up a minute. I'm sorry. Let's not use a combination of the top and bottom functions, but instead just use the top. So 8x squared, thank you for that, over 5 plus x. Slightly would be less of a miracle now. So we have 8 times 25 over 5 plus 5. 8 quarters is $2. That's about the arithmetic that I can handle. Divided by 10. Well, how about that? Happens to be the same. So the two-sided limit is equal to what? 20. And what is the value at 5? Well, to compute the value at 5, I use the bottom function. See, because of this equals right here. So when x is actually equal to 5, I use the bottom one, and that's 5 squared minus 5, which magically is 20. So is this function continuous at the breakpoint? Yeah, it actually is. It actually is. I'm going to take a picture of this. This is a good one for me to stick in the extra materials. Yeah. Oh, I haven't even touched that yet. So that these two kind of go together. It's 5, but you're right. I'm going to have to look at negative 5. Yeah. All right, sorry, I have to open my phone. It doesn't recognize me. That. And we can close that. Okay. So good. What's this answer here? 20. What's this answer here? 20. Now your problem might be different. Your problem might be discontinuous. Or it might be continuous. I don't know. Depends what numbers they stick in there. Okay. So make sure you do your particular problem. So it's continuous at 20. Is it continuous everywhere, the function f? No, because the top function has a vertical asymptote at -5. So if we're looking from like, minus infinity to infinity, this point is actually okay. That's what we found out. Nothing bad is it could have been bad, but it's not bad. But this point is bad in kind of an infinity kind of way. Okay, the function is bad there. So the intervals where it's continuous is everywhere here and everywhere here. So here's a problem. They want you to describe your answer using interval notation. I'm not sure what's going to happen here. Oh, yeah. Did I properly use interval notation? No, I mean, I did, but what should I put here? Union. I don't want a union. I guess if I union them, it's still the same. Maybe WebAssign is going to let you put the union symbol between these two, right? But if one of these were closed, then the union would actually just be everything and we would lose some information. So when that's going to happen on your assignment, but I guess it doesn't matter just yet. So you can probably enter this one with the union. Anyway, I'm just going to take a picture of this so I can add it to the other picture. You see people are texting me about the meeting. All right, that's okay. We're going to come out on top eventually. We are. Okay, any questions about this one? Or what about that one? So if we look down at the bottom, at x equals 5, what is the correct answer? Is it left continuous only, right only, continuous, or nothing? Continuous, exactly. And how about at minus 5? Infinite. Yeah, something bad is happening there. And I just want to remind you, you can graph this function. Even in Desmos, there's a way you can graph a piecewise function, or you can just graph the pieces and look at the two pieces, right? But notice I didn't do that to solve the problem, right? I had to think about the situation to solve the problem. And that's important. Again, because math people like abstraction, like someday you might need to answer a problem that has like weird parameters in it or things you don't know and analyze that, but you can't just graph it, right? And that might happen to you in the sciences when you do science. I don't really know how science works, but I imagine that you analyze things, right? Model situations. So that's basically what we're doing. We're thinking about what this function is going to be like and what could happen to it. Okay, that's number 25. We did this one. We did this one. Oh yeah, and someone said I can't figure out how to do the intervals. Again, I think WebAssign is going to want you to put a union, but in at least one of these problems, I think you're going to have to put a comma to list them. I think that's what's going to happen. Yeah. It would be like in here. And so you would type this interval, and then when you get to the union, that little calc pad, oh, maybe I can make it pop up. That little calc pad that pops up here. Anyone know off the top of their head where it is? Oh, sets, I bet. Yeah, you would type that thing in the middle. So I'm not actually allowed to, can I use infinity? No, I actually have to go find infinity. Whatever. Okay. I can type in what? INF. Okay, thank you. That's very helpful. Oh, okay. That's cool. Let's try that. I want to see that. -5, INF.
Sorry, infinity.
Oh. Oh, okay. In the program I use, it's called inft. So I was trying to type inft. Anyway, something like I'm not allowed to press submit because I'm the instructor. But that is what you would type there. Okay. Yeah. Oh, poop. You know how I type the union symbol and then I type stuff around it? I have found that sometimes that causes an error if you happen to do that. Sometimes you just have to erase everything and try that again. You could also try comma, but we can look at that. Like it could just be a typing in error, right? But yeah, it's a pain and I'm sorry for that. All right, the last one is 19. I think this one we should get up at the board. This one is an algebra problem, but it's tricky because as x goes to 3, what is the top approach? 3 minus 3, which is 0. What is the bottom approach? 0. Do we like 0 over 0? No, we do not. We do not like 0 over 0. We don't know what it is. It could be 2. It could be infinity. It could be pi. Could be negative 17.5, could be negative infinity. Did I already say 0? Could be that. Okay, we just don't know. But we really don't like that. We don't know what that limit is going to approach just by looking at the point, right? Because the limit isn't about at the point, it's about nearby. So you need to do some algebra, but what algebra to do might not be clear to you. So there's a couple different ways you can approach it. I'm going to let you guys work it out on the board and see what you could do. I also want to point out, why does it say plus? Why couldn't it just say 3 here? coming from the right. Can I come from the left? If I come from the left, I'll have a number like 2.9 or something here. And then when I subtract 3, I'll get a negative under the square root. So this function isn't even defined to the left of 3. There's nothing over there. It only starts being defined strictly after 3. Okay, so that's why we're only looking at the limit from this side. So but the algebra here is a little nasty. Why don't you go ahead and get up? There's a board there, 2 in the back, 1 here, people in the middle, choose your side. And we'll try to do this problem right here. Well, here's the sad thing though. Can you write like 2/3 on the board? Like anywhere, like 2/3. All right, and then square that for me. What do you get if you square it? Is that equal to 2/3? Uh-oh.
Yeah, actually,
Yeah. So you can't square a fraction because it's the same thing that you have. Super-temporary, so you can't. So you have to find a different algebra. You did get the right answer.
Yeah.
But the half wasn't. No, but that's a lucky algebra. Yeah, because that's not equal to the other. This thing happens to have a big limit.
I used to say
I forget how to do it all.
multiply by.
I'm not trying to figure it out on the stage. Like that's really
got it.
lucky to square a thing. Everybody's looking at your board because they don't know what to do either.
Negative. The reciprocal.
Oh, you did the same thing, you squared both sides, is that what you did? Or you multiplied, I don't think you multiplied the bottom correctly. The square root of x minus 3 times x minus 3 is not x minus 3.
I got it. Right.
Yeah, so that algebra is not right either.
Reciprocity. What I called it.
Reciprocity? Well, I agree that you can multiply the top and the bottom by the same thing. I agree with that. And I agree that then you, yeah, that's a nice way. Let me just, yeah, this is one of the 2 ways I would think to do it. Can you just put the limit in front of it so that you're doing the calculation there, like throughout the calculation? And make sure everyone at this table understands this.
So.
I mean, like, I know what
See everybody looking, go ahead and take it. See if that helps.
We see that.
Couldn't it like not?
Yeah, I like that.
Proper way. I thought
I
it was
put
the
some
left.
parentheses around here.
Yeah. Only on the bottom. Yeah.
Yeah.
Only
Like,
the limit could be 0, but when it's over 0.
Yeah.
But if I multiply by the denominator, fine. That's just a thing that we see.
But we don't know what that is. It's not necessarily 0. We had one problem where 0 was 2. So 0, we just don't know what that is. Sometimes it works, but in general, it's not. 0 is terrible.
Yeah, no, I mean, like, I really understand.
Like, okay, here's one. I got one for you. What if this square root wasn't here, right? Then you'd still have 0/0, but the limit would be 1 because the 2 pieces just cancel out. So that's a 0/0 that's equal to 1. Just trust me, 0/0 is bad, very bad, the worst bad. Yeah, on the back, are you happy with this?
Yes.
So this way, what would make you think to multiply by the square root? I mean, besides the negative, right? But like, what would you think of? So we can think of multiply by one. We hate square roots. We hate square roots. One way to get rid of square roots is to multiply two of them together. And you're allowed to multiply by one. So that's what I think. How about y'all? You happy with that? You also hate square roots? Yes, I hate square roots. The hard one. So that's why you multiply by this root x minus 3 over root x minus 3. Because it's going to kill your square roots. And then let's look at something here. Squaring it, squares the top, squares the bottom. Earlier, I made that for example, 2/3 squared, and that's 4/9, but that's not equal to the original. So you can't square. Here, you multiply by 1. So you put anything you want here, anything you want here. And multiply by that is multiplying by 1. That's it. And are you all happy with the canceling? Right? I know. That's why this one is hard. I agree. All right. Let's talk about it. So let's go over this one. So we have the limit as x goes to 3 from the right of x minus 3 over the square root of x minus 3. This approaches 3 minus 3 over the square root of 3 minus 3, which is 0 over 0, which is very bad. Okay? We don't know what it is. Maybe this limit will end up being 2, maybe it'll be 0, maybe it'll be infinity, maybe it'll be 1. I'll show you in a minute why it could be other things. But it's not clear what algebra to do at first. And because there's nothing to cancel, there's nothing to multiply out. And you have to like have a gut instinct sometimes for algebra. And my gut instinct is I hate square roots and I would like them to go away. Okay. How do you make a square root go away? Well, one thing you could do is square it. I saw a few groups saying, maybe we can just square the whole thing. And that changes the fraction, right? That's not equal to the original thing. Like 1/2 squared is a quarter. You changed it, right? So you can't just square the whole thing. But the other thing you can do with square roots is multiply them by themselves. The whole point of a square root is that it's a number whose square is the thing inside, right? And so it's hard to remember that actually, but I could multiply by root x minus 3 over root x minus 3. And this part here is equal to 1. I can multiply by whatever stupid clever thing that equals 1 that I want to. Okay. And this particular thing, and notice I'm writing the limit at the outside of each of these. Each group stopped writing at least one of these limits. And that's why I didn't take a picture of your board. I'm going to take a picture of this board. Because we haven't done the limit yet. We're just messing around with algebra. And so now we get x minus 3 times root x minus 3 on the top. And we get root x minus 3 times root x minus 3, which is x minus 3 on the bottom. Now, I think technically you actually get the absolute value of x minus 3. It doesn't matter here, and we don't want to get into that, but like, just know. There's a little white lie happening here, but it's fine. Anyway, now I actually can cancel. And remember, whenever we have 0 over 0, it means there's probably something we can cancel out to make our life better. And we did. Now that we've canceled, we can try it again. And we get the square root of 3 minus 3, which is 0. So there's a lot of ways to do this problem incorrectly and get 0, right? And that's lucky, right? But this is the way to do it and get 0. Yes.
So why does 0 work now? It didn't before. I didn't think we were allowed that.
Because there's no over 0. It's just 0, right? Here was 0 divided by 0. That's what made it sad. 0 divided by 0. That's just 0. That's fine. And the square root of 0 is fine. There's nothing wrong with taking the square root of 0, square root of 0 is 0. That's okay too. I'm going to take a picture of this if I can get my phone to recognize me. Here. For those of you that are thinking, well, are we always going to get 0 when we have a 0 over 0 limit? Imagine if this original problem had been upside down. So imagine if this fraction had been upside down. I would still have 0 over 0 here, right? The fraction was upside down. I'd have this, but upside down. I'd have this, but upside down. I'd have 1 over this. I'd have 1 over this. I'd have 1 over 0. That's like infinity. That's not like infinity. Okay? So we can't tell just from seeing 0 over 0 what's going to happen. Does that make sense? Is that why you did that?
I have a question.
Yeah.
What is this? Alphabetical?
I would say that it's called multiplying by 1 because it needs square roots. I'd say it's multiplying by a special form of 1. People call it that a lot. Multiplying by a special form of 1. It's not multiplying by a conjugate. If that's what you're thinking, there's this trick. That might be what you're thinking, is that there's a word. That word is if you have like x plus square root of 2 and you would multiply by x minus square root of 2. Like, well, yeah, like the next one. That would help with the next one, actually. Yeah. Yes.
So is the new one that we got, the one that the question 3, is that the same as the first one?
Yeah.
So,
This limit here is, I'm glad you asked that exact way, because we were given this problem and I complained when multiple groups squared the inside and I said, well, that's not the same problem anymore, right? But this is the same problem because of that cancellation theorem. We had a theorem that said that if you do algebra and along the way you make a cancellation that only affects this one little point right here that the limit is approaching, this limit will equal that.
so then, still don't understand why it's okay for it to be 0.
Well, it just is 0. I mean, I don't know if it's okay. It's just like it is, right? But that's no, it's okay because it's a number, I guess I would say. So when we plug in here, you know, when we plug in to do a limit, that's like we're hoping that something nice is going to happen. And nice would mean the answer is a number. But our hopes were dashed. No hope. No. Okay. At least here. There's no hope over here. But then we do some algebra, and now there's hope. Now we can plug in and get a number, right? So I guess that's really the point. If we plug in and we don't get a number, then that solving method is not working for us. So we have to change the limit in a different form so that that solving method can work for us. All limits are going to end with you plugging in at the end, right? All limits are going to end with like, okay, this form didn't work, but I can rewrite it, and now I can plug in. That's how it's going. I don't want to say there's no hope. That's just too sad. I'm going to say, oh no. Oh no. Because the next thing that happens right here is algebra, right? That's always what happens after here, until you learn this magical thing called L'Hopital's rule, which you will see in 232, and everybody loves too much. If you know L'Hopital's rule now, not going to help you now. Okay, don't use it. Okay. More questions about this. These are great questions. Let's see what else we got. Well, we don't have any more. I want to look. Hold on. What was that? 20. This is number 25. Oh, here we go. This video here is very good. So this video by Nancy. I love this board that she has that she can write on. Do you guys know how this board works when she writes? Can she write backwards? What's she doing? Well, we have one of these boards at the department, and not the department, in the library, and I was so impressed to find out that she's not writing backwards. She's standing behind a glass board, and she's writing normally, and they're filming her, and then they flip it. They just flip the video. So if you were in the room with her, it would all be backwards. But then when they show the video, they flip it and it's forward. So you're actually seeing her flip the way she'd see herself in a mirror, right? Instead of the way she'd appear on camera. I think that's really cool. But look at her, she's talking about plugging in, right? That's something we have to do. Factoring, that's something that happens a lot. That should look familiar. Common denominator, look at this limit. You've seen ones like this, right? Right? This is a very, very, very relevant video. Let's see what else happens. Can you pause this though? Oh, look at this. You saw one of these the other day where you couldn't cancel. Instead, you had to open it up, right? You had to expand it. And then you had to do it. And let's see what else she's got. Oh, that's it. We love L'Hopital. Someday we will. All right. I believe that's enough for today. Can you please erase your boards? Good luck this weekend. Let me know if you need anything.
Did you want to look at my website?
Yeah.